Hi, I'm Hallie, and welcome to Project Str-Eng. Lots of questions surround the structures in our world, such as who made them, how they made them, and why they made them. And Project Str-Eng is our attempt to find these answers through understanding structural engineering. In this episode, we're trying to understand shears. But first, let's talk about history. From the scissors in your kitchen to the hedge clippers in your garage, shears are an everyday object that some unknown ancient engineer really clutched up with. Although we're lacking receipts on this, it is believed that the earliest known scissors were invented by people during the Mesopotamian period 3,000 to 4,000 years ago, though they've advanced greatly since then for more uses, because the earlier ones were essentially just a U-shaped piece of metal used to cut the skin and fur off of animals. Yikes. Now I'll pass it off to Peyton with the interview.
All right, shear.
Shear. What is shear?
Shear is forces acting along a plane. Shear is a fundamental thing, and it's tricky. Engineers are confused by shear. Shear is less obvious than pulling or pushing.
Yeah.
It's a tearing force. It's a sliding force.
So I was gonna say, when I imagine shear, I imagine a pair of shears.
Absolutely.
Would you say the shear force is similar to kind of a...
That's why they're called shears. Shear is a planar stress, which means it acts on this plane. So if you think about that plane or that joint, I can move it back and forth, I can move it left and right, but typically in engineering, or at least structural engineering, I would like it to not move. So I have to design that joint so that I'm resisting that motion. Like for example, this stack of papers is 1,000 joints all stuck together. And to know which particular joint is going to slide is often not the goal. We don't know whether the joint will appear here or here or here, and it has something to do with how the individual elements have been aligned in this stack. If I'm applying across this plane a shear force, you can see the pages slide until I create a failure plane. This was my first failure plane, but there's also secondary failure planes where my applied force is too much for the inherent resistance of the paper. Often we define failure as movement.
Because we don't want structures to move.
Precisely. One of the places where shear is very important is if you have a bridge or a beam or a lintel or a whole bunch of different types of things, we often are used to thinking of them as bending elements. So if you have a long bridge, you don't want it to snap in the middle. But another very important type of failure to consider is a shear failure at the supports. These are individual blocks held together with magnets, but if I put a load on it, a rock is a good load. When I failed this, it failed at the support. If it was longer, it might have failed in the middle and it would be a bending shear due to too much moment. But because it's sufficiently strong and beefy and thick in the middle, but here I have a shear failure all primed and ready to go, that's why you'll often see support thickening at the edges. So that's one of the benefits of an arch. An arch is slender in the middle and it thickens at the edge, because masonry is very similar to a children's building toy. It is individual units that are individually really good at compression, at squishing, and typically we know that it's bad in tension, so we don't use bricks as ropes. Bricks come with their already built-in shear failure planes, and they tend to be really bad in shear. So what we end up doing is we can build an arch. Now look at this, all that shear failure has been bridged. In engineering, there's a need. A client needs something, and we are coming up with the most cost-effective, best, safest way to meet that need while satisfying all the constraints. And an arch often exists because you need to go under it, or you need a window, or you need a door. And so I'm not allowed as an engineer to just fill this space with concrete. That would be great. Fill it with dirt, fill it with something, right? If you don't want this to collapse, put a thing there. But if I'm constrained and I need to have people walking through my arch, I can make it stronger, and now I have twice as much material bridging my shear failure zone. I have so much extra material here at the supports that I can distribute my shear and average it out across this larger space. So even though my force is the same, my stress has been reduced because it's got a larger area to distribute over. So now I can apply that same shear force, and it requires a lot of effort to induce, again, shear failure. See, there's your two failure planes. Still failed in shear. There was still a shear force applied, but now the capacity of the structure or the element was doubled.
So where does shear appear in everyday life?
If you park in a parking garage, look up, because concrete spans a long distance. It's really great material for making parking garage slabs, or even slabs in an office building or a condominium. In order to minimize space, we make concrete slabs as thin as possible, but thin is really bad for shear, because this is a perfect demonstration of what shear is. There's a small little plane right there, and I can induce failure right at that small little, that's a shear failure. When I'm designing a concrete building, architects really appreciate it when I have slender columns, and architects really appreciate it when I have a slender slab, because I have high ceilings and I can fit more floors into a high rise. And when I put a slender slab on a slender column, there's stress concentration, and that column wants to poke through the slab until the slab pancakes the slab below it, and that's generally considered to be bad. Is called a punching shear.
Punching shear.
Because the column has punched through the slab. This is my model of a bridge. I have a truck that I want to get from one side to the other, that I'm now worried about creating a shear failure zone at the support. Pure, clean 2 shear failure zone. I've got 2 zones that I need to worry about. Just like a bridge takes you from side 1 to side 2, we sometimes talk about bridging when we're talking about shear failure, because now instead of saying side 1, side 2 of my bridge, I'm talking about side 1 and side 2 of my shear failure zone. And so what I can do is I can add reinforcing steel. If this is my concrete bridge, my daughter's not going to like this. I have reinforced the shear zones. Shear still exists, but now it's in a zone that I'm less concerned about, because there's less shear stress concentration away from the supports. So I can allow my middle to be less reinforced and save money on reinforcing steel. And I can still drive my truck across without causing a shear failure. Shear!
So basically, the magic behind shears is in the fact that the forces are unaligned. Essentially, they're moving diagonally across one another or in 2 different directions. The simplest way of explaining this act of force without scissors is by taking a piece of paper and ripping one corner in 2 different directions until it rips in half. The paper tears as a result of shear forces. The word shear is a reference to the fact that such a force can cut or shear through the surface or object under strain. Bending moment and shear force calculations are essential in designing anything structural. Who knew scissors had anything to do with skyscrapers? Do you 2 know each other?
What's up? What's up?
Does your brain feel bigger after this? I know mine does. Thanks for tuning in. Remember to smash that like and subscribe button on your way out. And as always, enjoy the process.
Oh yeah, that's good. Feel free to use that. Sheer goodness! Want to do that again?
Sheer goodness? Sheer goodness! I thought we were saying sheer goodness for